Okay, hi everyone. Welcome to our next press conference. This is the Dawn Science Update. Our participants are Raymond, Tom Prettyman, Norbert Schorghofer, and Ralf Jaumann. Go ahead.
Good morning, everyone. Thank you for coming to the Dawn Press Conference. I'm Raymond. I'm the Deputy Principal Investigator. And today we're going to present some major new findings from the mission. But before we get started, I thought I'd give you a status report on where Dawn is now. Dawn completed its primary mission in June of 2016, excuse me. And we are now in our extended mission phase. And Dawn completed this ambitious mission to survey two objects in the main belt, Vesta and Ceres, and was a historic mission in the sense that it was the first to go to and explore two separate targets in the solar system. So Dawn has returned copious data from Ceres, 54,000 images, millions of spectra in both the visible and infrared wavelengths, which we use to determine surface mineralogy. Today you're going to hear about the abundant gamma ray and neutron measurements that Dawn made. We have spent 8 months in low altitude orbit collecting those data, and they are really very valuable and very good data. Gravity field was mapped using our radio frequency tracking system, and we now have a gravity field to about 65-mile resolution, which was way beyond what we had initially expected. And we've used image data collected at different illumination directions to create a topographic map that is good to about 65-foot height accuracy. So we have a very comprehensive view of Ceres now from this complete data set. So as I said, we are now in our extended mission. We have raised the orbit from our lowest altitude in the primary mission, and we in our second extended mission orbit, the purpose or the objective was to look at some targeted areas that were of interest in different viewing conditions. And one of those areas was Osho Crater, a small crater in the northern hemisphere, in which it was ice had been detected by the infrared spectrometer. There are bright deposits in the crater, and the spectra of those bright deposits indicated water ice. And you'll notice that this water ice deposit is at the edge of the shadowed crater wall. North is in this direction. And because the ice is not stable on the surface of Ceres, we believe that this ice was exposed by a recent landslide, which you can see by the deposit, which has slumped down into the crater floor. So this is one of the really interesting areas that we discovered, and we followed up on in the second extended mission orbit. We also targeted other areas where craters were in persistent shadow, and you're going to hear about those from Norbert today. Dawn is currently in its third extended mission orbit. It arrived there on December 5th. It's at above 7,500 kilometers from the surface of Ceres. And the main objective in this orbit is to obtain background data for the cosmic ray background so that we can improve the signal to noise in the grand measurements and do an even better job in understanding Ceres' surface and its origin. So I'll leave you today with some thoughts on the overall goal of the mission. This is just to remind you that the Dawn mission is trying to look back in time to the very earliest stage of the solar system, and we're interested in what was happening when Ceres, right after Ceres accreted, and we are mostly interested in whether water and rock, or the water and volatiles separated from the granular material, created a subsurface ocean, and the water and rock interacted in ways that would have produced a chemical environment which would have been conducive to life, a habitable environment. We can't investigate the habitability or the habitable environment of of Ceres other than to look for the chemical fingerprints on the surface and the shallow subsurface to understand how that may have occurred. So we have ample evidence to say that the presence of the subsurface ocean was likely, and you're going to hear from Tom today about some of that evidence. So we're hopefully you'll agree with us that Ceres is a really interesting object, which is going to help us to better understand many of the objects in the early solar system, as well as the processes which are occurring. And so with that, I will turn it over to Tom.
Thank you very much, Carol, for the introduction. I'm going to talk a little bit today about results from the grand investigation at Ceres. We've completed our analysis of the primary mission data, and I'm very delighted to say that the analysis will appear online in Science today. So let's start out with some data. And as I get into this, I'm going to start by describing what GRAND is. It's a gamma ray and neutron spectrometer. So where do gamma rays and neutrons come from? There are two sources that we see with GRAND in orbit. One of them is from galactic cosmic ray interactions with the regolith of Ceres. And so you can imagine high energy particles whacking into the surface, breaking apart nuclei, and producing a spray of secondary particles that include neutrons. The neutrons rattle around in the regolith. Some of them escape into space. Of course, the regolith is the loosely consolidated soil on the surface of planets. And the neutron emissions are sensitive to light elements like hydrogen and carbon that's in the surface. The neutrons also undergo nuclear reactions and make gamma rays, and the gamma rays provide a fingerprint of what's in the surface. And so you can kind of imagine that there is a specific gamma ray energy associated with particular nuclear reaction. You know that energy, you can identify the element that was struck by the neutron. So we're in orbit around Ceres. We're about just a little less than a body radius altitude away, and we can see these emissions coming from the surface. We can measure and map the gamma ray and neutron emissions on these bodies. And what we find is shown in the video to the left, and this is a comparison of the concentration of hydrogen on the surface of Vesta and Ceres. And you can see that hydrogen is being displayed as a weight percent on both, and that the color scales are the same. The craters in the background are not what we measure with GRAND. Our resolution is too blurry. They're just there for context, so you can kind of see where the hydrogen is. The other comment that's important to understand is that we are not sensitive to the chemical form in which hydrogen appears. We're sensitive to hydrogen, or if we're measuring iron, we're sensitive to iron. We're not sensitive directly to H2O, and we have to infer the presence of H2O via other models, and we'll get to that in a moment. Not good. Let's see. There was a problem with Microsoft PowerPoint. It closed. Sorry for the inconvenience. How shall we extricate ourselves? Oh, it's jumping up and down. I'm not a Mac user, so let's now try and restart the presentation. Maybe it will restart. Yeah, sure, why not? So back to our movie. So I think I've made that point. So the hydrogen variation is actually the color variation that you see. So look at the scales. Vesta has very, very little hydrogen. It's mostly a basaltic body and underwent kind of magmatic differentiation. It's the fiery end member of the bodies visited by Dawn. Ceres, on the other hand, look at its scale. The average is over 100 times more hydrogen than you see on Vesta. And in addition, on Vesta, the hydrogen distribution is kind of patchy. You've got a hot spot near the equator where you had carbonaceous chondrites impact the surface, whereas on Ceres, it's very uniform, and there's a latitude variation that's very pronounced. The uniformity is taken to mean that processes that produced the hydrogen, or the water, as we'll see in a moment, acted globally on Ceres. So now I'm going to take the hydrogen and I'm going to do something. I'm going to multiply the hydrogen content by 9, because I'm going to assume that hydrogen is all in the form of water. That's the next picture. There it is. And you can see that in terms of water equivalent, Ceres hydrogen content varies from about 16 weight percent to 29 weight percent. Now this means something to us, because Ceres' best meteorite analog are the carbonaceous chondrites, and they underwent liquid processing in the interior of their parent bodies. And we think that Ceres was also processed by liquid water. And that makes hydrated mineral assemblages. And the equatorial region on Ceres is very similar to what we would expect if you had hydrated minerals and organics. Above that, you're probably looking at water ice. And so the model that's most consistent with the data that we see involves pore-filling ice. This is 4.6 billion years ago. You might have had an initial condition where the regolith was icy. The sun warmed the equator more than the poles. And as that happened, you start to remove the ice from the surface. It sublimes, and the ice gets deeper, deeper, so on, so forth, all the way up to the present day. And so it turns out that so the darker color that's being shown there would be ice-free soil, but it would be loaded with hydrated minerals sourced from the interior. The ice is probably also sourced from the interior. We don't think that it is exogenic. That particular curve is the best fit to the grand data. It implies a regolith that has fine particle size, low vapor diffusion coefficient, consistent with the meteorite analogs. What isn't consistent with the meteorite analogs is other elements such as iron. If you look at the elemental composition of Ceres, it bears some resemblance to the carbonaceous chondrite meteorites. But there are differences that support the idea that ice and rock that came together to form Ceres actually separated in the interior and were redistributed by processes like convection. And this cartoon just illustrates that. Here you are beginning in the solar nebula to grow Ceres. It's small. When you have a small body, it's hard to set up a convection cell, and you have alteration of minerals in a closed system. Elemental composition is constant in that case. That's very similar to what we think has happened on the CI parent body, the carbonaceous chondrite parent body. For those of you who are interested, I brought a carbonaceous chondrite with me, so you can look at it afterwards if you like. So, but as time goes on, as you build up more material, the radioactive heating tends to drive convection cells. You get formation of mud, liquid water, that moves around in the interior, redistributing the elements. You might get radical structure, differentiated structure, where you have a rocky core with a mantle that's hydrated silicates and ice freezing over a briny liquid layer. That's one of the scenarios that we want to test on Dawn. And then somehow that disappears over time, maybe through impacts and sublimation to bring us to our present state. So the grand data support the idea that is also supported by gravity and to some degree by mineralogy, that Ceres must have undergone some degree of internal differentiation. And now I'm going to turn this over to Norbert. He's going to talk about ice in different contexts on Ceres' surface.
Thank you. So this here is a sequence of images taken by the Dawn spacecraft of a crater near the North Pole. And it captures a whole solar day on Ceres, which is about 9 hours long. And the floor of this crater doesn't see the sunlight. And these images are actually taken close to the northern summer solstice, which occurred on Ceres in July 2015. And so the sun never gets higher than that, much higher than that. And so this is shadowed throughout the entire Ceres years, and it's therefore very cold. And because it's so cold, ices, which if there are ices in there for any reason, they would last because we evaporate so slowly to space. So we refer to this sometimes as Ceres' darkest secret. And we now know the answer, and it appeared in a paper in Nature Astronomy, which I think was released today. But first, let me show you a map of all these persistently shadowed regions, or sometimes we call them permanently shadowed regions. Either way, we abbreviate them with PSR. And so this is a map of a North Polar region of Ceres with a North Pole at the center. And the way it's made is just by using lots and lots of images, all from near summer solstice, and stacking them and keeping the brightest pixel on top. So if it's still dark, then this is a persistently shadowed region. And so there are over 600 persistently shadowed regions, almost all craters, in the northern hemisphere of Ceres. The total area is about 2,100 square kilometers. And here now, where there is more photos. So the first panel in A, that's a regular image, again, of a crater near the North Pole. And B, below, is the same image, but stretched. And actually is scattered light, enough scattered light, indirect sunlight, so we can see what's inside of these otherwise shadowed, of these shadowed areas. And there's this bright deposit on the floor of this crater. And the second row here, CDE, that's another crater. So C, again, that's a regular image. D, that's an image, same image, but stretched. So there is, again, a bright deposit with green arrow shows points to a bright deposit on the floor and wall of these craters. And only a few craters, only a few of the PSRs, I should say, have bright deposits. Most are empty, a few have them. And in E, again, still the same crater, but the bright deposit actually sticks out into sunlight. And that allowed Dawn to acquire a spectrum of this and identify its chemical composition. And it's water ice. So this bright deposit has been identified, is identified as water ice, and therefore we assume the other bright deposits in PSRs are water ice as well. Now, this is just an illustration of how we believe water molecules end up in these cold traps. So permanent shadowed regions are cold traps, almost synonymous to them. And so what happens is if, for whatever reason, there's a water molecule on the surface, it will undergo this giant hops, which take over an hour. And a fraction of them, a small fraction of them, will just happen to fall into cold traps. So that's how we ice, we think how the ice in there accumulates. And now this is a map of the entire northern hemisphere of Ceres. And what it shows is two spots. Two spots are labeled. These are the only two spots where water ice has been identified on the surface. So as Tom Prettyman showed, there is lots of ice beneath the surface, very close to the surface, but it's rare on the surface. So subsurface ice is ubiquitous on Ceres. Exposed ice is rare. And so as PSR number 2, that's the crater I showed on the previous slide with a bright deposit. So this is the only exposed ice in the northern hemisphere of Ceres. Now, Ceres isn't the only body in the solar system with cold traps. Mercury has them, and the Earth's moon has them also. So what's common among its three airless bodies, is that they all have low axis tilt. So there's very little seasonality, and a crater near the poles doesn't see sunlight. So we can, Ceres helps us to put Mercury and the moon, or a cold trap of Mercury and the moon, in context. And in Mercury, the cold traps are basically filled with ice. On the moon, the situation is very complex. There doesn't seem to be much exposed ice, at least. And in Ceres, there's ice in some cold trap. And so is the source of this ice the same in all of these? We do not know the answer, so there's various possibilities for the sources. It could be ice fallen onto these bodies from space. It could be solar wind generated, or in the case of Ceres, it could be its own ice, because even dry impactors can excavate some of the ice in its ice-rich shell. In any case, the cold traps of Ceres show us that ice does get trapped in these cold traps. And so I think we understand this much better. And I turn this over to Ralf Jaumann, who will show you a different type of bright deposit.
Yeah, I will show you one of the most amazing features on Ceres, and I think it's also one of the most exciting impact craters in the solar system. It puzzles us since we approached Ceres because of its bright dots in the center. Okator is a 92-kilometer large impact, has two bright areas which are called facula, Cerealia facula and Venalia facula. The distance is about 2/3 of the San Francisco Bay Area. And the other puzzling thing is we really see two colors, a bluish and a reddish color in its interior. And it's fairly deep. It's about more than 5,000 kilometers. So the question is not whether it's an impact or not. The question is where is the material inside this impact is coming from. And there are different materials. So we have materials which are coming from the walls, from the rims, which are going inside. We have materials which are on the crater floor, but it's flowing to the crater rims, which is of different color. And we have this. That's the bright spot. That's the bright material in the center, and you can clearly see the bright material in the center. And now we go to lower contrast of the surrounding and higher contrast in the center. We have a depression in the center. This depression has a dome in its center. Material is also on the dome, on the depression. It's coming from the rims. The depression, the dome itself has two colors. It has some kind of reddish color. In the meantime, we really know that the dome is composed on carbonates. Carbonates are salts. Fortunately, they are spectrally active, so we can find them. But there may be also other salts. But if you look at this too, you really will understand that this is a very perfect science investigation which brings together mission operations and camera operations. And that's unique. I think I never have done this before, and it works perfectly in order to do the three-dimensional images. And what you have seen is based on about 2 billion object points. So we have the information of 2 billion points about its exact position on the surface and also of its height on the surface. So that's a real big issue, that a real big thing Dawn did, not only for Ceres, but also for Vesta. And you can download the movie on JPL NASA Gov together with the music I didn't show you or let you hear. Thank you.
Okay, so now we'll open up the floor to questions.
So, Okator, before you sit down, what is the current take on it? The last I heard, those were thought to be salt deposits, like you have in Iran. Is that still the theory? And I mean, what is the current take on what those bright spots are and how they form?
Okay, I think the question is not really solved yet. We know that there are carbonates in it. There are magnesium-rich carbonates in the bright spot, so that's some kind of dolomite. It's not completely clear how this built. And the big question is you have to do some separation of the material. We know that the surface is mostly phyllosilicate, so that's clay. There is salt in the surface and in the subsurface, but you have to process it in order to get these bright spots. And it's not completely clear what this process is behind this. There are two possibilities. They are still discussed. One possibility is we have impact melt. We have a large impact melt pool in this impact crater, and there is heat in this material, and then there is some hydrothermal processes because we have water involved, and that results in a separation of different materials, including the carbonates. Another idea is that we have material beneath the surface which has been released by the impact itself. So it's impact-triggered cryovolcanic activity. There's an open debate about this. It's not clear how this works. There are a number of issues we have to consider. One is there are other impact craters which don't show these features, which don't show these effects. So maybe there have been different impact velocities, but that's unlikely. On the other hand, we have this Ahuna Mons, that's the mountain we see there, which has similar features in spectral characteristics like this interior of Okator, but it's not impact triggered. So there are two possibilities which we really have to understand, and in order to get this, we have to understand more about the surface chemistry, and there are still data not evaluated, and we also have need more understanding about the subsurface structure of Ceres. So we have a good overview over the whole structure, but not over the structure in the subsurface, let's say the first 10 kilometers or 15 kilometers of the subsurface. And there needs to be some modeling, because the data alone give you not the right answer, so we have to understand the data and we have to model it in order to understand whether it's cryovolcanic, it's impact-triggered cryovolcanic, or it's only impact.
Okay, any other questions from reporters in the room?
Kind of a follow-up to that question. I remember when Dawn was still approaching Ceres, there was a lot of talk about how these bright spots might have been water ice, and then you got the better data and determined that they were in fact salt deposits. But now you're finding that there are water ice deposits in at least one and perhaps more of these shadowed craters. So I guess my question is, do we think that the water that is now in those shadowed craters, is it possible that that was originally excavated to the surface with the material in the bright spots?
Probably yes, because the water we find, for example, in Oxo crater, that's very close to the surface. So that's a desiccation of the surface by sublimation, and the water is whatever, half a meter below the surface. We don't see it. I'm pretty sure that there's also water in Okator in the subsurface. But the question here is, the problem we have is all our instruments are not able to penetrate the surface. So we just get the first, whatever, millimeters of the surface in our data.
Okay.
Hi, I'm Alex Witzy with Nature. My question is for Carol Raymond. I wondered if you could just talk comparatively a little bit about Ceres versus Vesta, now that you've sort of had time to think about Ceres as a world, and what similarities both bodies have and what differences they have. Can you just sort of talk in a qualitative sense about how you see those worlds?
Sure. So Tom did a good job of talking about the hydrogen content and interpreted to be water content. And so generally, Vesta is a very dry object. And we've taken away two things from the investigation of Vesta and the confirmation that it's the parent body of the HEDs. And one is that it looks like it accreted from volatile depleted feedstock. So it probably formed in the inner solar system. We know it incorporated short-lived radionuclides, aluminum-26, melted, forming the core. So one big difference between Vesta and Ceres is that Vesta fully differentiated, and there's very few volatiles in the interior. or it's relatively volatile poor compared to Ceres, and yet Ceres may have formed nearly contemporaneously with Vesta, based on the emerging models of pebble accretion and the understanding of the building of planets from planetesimals. So Ceres may be fairly close in age, but obviously it did not melt, and so its size may have something to do with that. The efficiency of convection may have dissipated heat fast enough to avoid the object fully melting. It looks like it formed further from the sun, or formed and evolved further from the sun, so that would have had some effect. But in general, the difference is that Vesta is much more akin to a stony, ordinary chondrite terrestrial planet, and Ceres is much more akin to the carbonaceous-rich asteroids, as well as icy moons in the outer solar system. So Ceres is very transitional, whereas Vesta seems to be clearly a cousin of the inner planets.
Okay, do we have any more questions from reporters in the room? We have a question from the chat.
We have two questions from Eric Berger at Ars Technica. Eric Berger asks, the first, is there any liquid water remaining inside Ceres, and if not, when did the planet freeze entirely? The second question, what is your best guess as to potential habitability in the past?
I'll start. So the geologic activity that Ralf was talking about does tell us that there's likely some liquids in the subsurface. Whether we have water is unclear, because what we would expect is briny fluids, and they have a much lower melting temperature than ice, than water. So the water likely is sequestered in the ice deposits near the surface that Tom's talked about, that Norbert's talked about. And if there are fluids, they're most likely very brine-rich fluids, and they would account for instance, the Honolulu's feature that's interpreted to be a cryovolcano. So yes, we do suspect that there are some fluids in the subsurface, and when Ceres froze out, would have been likely fairly early on, model dependent, but within a couple billion years of its accretion. And so before the freezing part, if there was substantial water rock fractionation and there was a substantial water ocean, then all of these chemical processes that were occurring that was creating the phyllosilicates we see would have provided the energy and the environment that would have been conducive to life. So I think it's pointing towards Ceres being an interesting object, mostly equivalent to Europa or Enceladus in terms of its habitability potential.
All right.
Yeah, Rick Lovett again. I have two unrelated questions. One is, why is it that all of the cold traps aren't filled on Ceres like they are on, I thought that would be on Mercury. Can you speculate why? Because it seemed like it would migrate uniformly if that's the...
So that's an important question, and there is work ongoing in trying to understand that. What might be the case is that the axis tilt of Ceres varies, and it was large in the past, and then many of the current PSRs become sunlit. So I think that's the at this point, and we are still analyzing data, but at this point that's it's a leading theory.
Okay. I believe we have one more question from the chat.
First question is from Paul Doherty at the Exploratorium. Paul asks, what do the gravity data show about Octator?
The gravity field resolution is just about sufficient to isolate a crater. And it's the subject of ongoing work that's soon to be published. So I think I'll pass on that question.
Okay.
My question is, what's the health of the spacecraft? There were problems with the reaction wheels, and I thought that you had a very limited life left.
Oh, fortunately, the 2 reaction wheels we had left have continued to perform well. So as you may know, we're using a hybrid system with the hydrazine jets and the reaction wheels that we have left. The fact that they have survived means we've used about half the hydrazine we would have had to use without them. So that's one of the reasons why Dawn has continued to operate, and those wheels, again, are doing fine. We're not using much fuel right now because we're farther away from Ceres, but as long as they survive, the prospects for continuing to operate are pretty good throughout the next year.
Okay, do we have any more questions from reporters in the room? Any more questions in the chat? Yeah?
We have a question from Tracy Watson at USA Today. Tracy asks, is there now definitive evidence of a past internal ocean?
Okay, I think I'll take that one. Liquid water had to be in the interior of Ceres in order for us to see the mineralogy that's on the surface, the phyllosilicates, and also the concentration of hydrogen that we see in the equator that's presumed to be ice-free. So Ceres surfaces, the fact that it's ice-rich and that there are alteration products on the surface means that at some point in time there was liquid water. Whether or not that formed a brine layer is still the subject of question. And we have a lot of data sets that we've discussed here that we're going to have to integrate in order to figure that out, if we can figure it out.
Okay, do we have any more questions?
Hi, just to follow up on that. When you say a brine layer, so that would have been perhaps quite a bit more salty than what we would consider a liquid ocean on Earth?
Right. Whether it's more salty and what its pH and what its chemistry would be like is not known. But what happens when Ceres forms is you have unaltered silicates and ice that came together. The radioactivity, the aluminum-26 that was present, warmed the interior and melted the ice. And when you have silicates and water together, you end up producing alteration products. It's a process called serpentization. Basically what happens is that the water gets incorporated into the mineral lattice of phyllosilicates. And so you consume some of the water in this process. Some of it is left over as water ice. Depending on the size, the permeability of Ceres, you could have formed convection cells. So the brine could have moved around inside of the rock matrix, transporting soluble elements to different places on Ceres, perhaps delivering water that froze to form an outer icy shell and having this brine layer. The actual composition of the brine is something I think that would need further work. But there have been publications in the past that were predictive that anticipated this layered structure that I mentioned. So.
And just to follow up on that, when the water freezes, it excludes the impurities. So the water, the ice will be pure water ice, and that means that as it freezes, the remaining liquid becomes more and more dense with impurities, which are the brines that create the brines.
Okay, do we have any more questions from reporters in the room? Any more questions in the chat? Nope. Okay, this concludes our press conference. We'll reconvene at 11:30. Thank you.